All right, hello everyone. Welcome back to another video for regression analysis. This week we're going to be going over chapter 12, which discusses all about logistic regression. 12.1 is just a little introduction. So far we have used y as the response variable, and it has been a continuous quantitative variable so far. We have also seen predictor variables that are both quantitative as well as qualitative. There are some situations in which the response variable is qualitative. The example that the textbook gives is used to predict job performance. So they used a scale of good or poor. And then another example that they also used was to determine the risks of cancer based on health records. And they used the response variable that the person either had cancer or did not have cancer. So instead of using numbers, we use words instead to scale our answers. Right, so 12.2 is going to go over how to model qualitative data. So the qualitative data, also known as the binary response variable in this case, can be coded with either a 0 or a 1. Instead of predicting values, we will try to model the probabilities that the response takes on one of the two values. So we are going to use pi to denote the probability where y equals 1 and big X equals little x. The model that the probability would come out to be in this case is depicted on the screen right here. So we're going to have our pi when the probability of y equals 1 and big X equals little x. Then we're going to equal this to beta sub 0 plus beta sub 1 times x. And then this this model of pi for the probability needs to be between 0 and 1. And also the assumption of equal variance does not hold in this case. All right, so section 12.3 is going to talk about the logit model. So the relationship between the probability pi and x can be represented by a logistic response function. So we can see that by this graph right here. So this model represents an S-shaped, with the probability increasing slowly at first, with the increase in x then increases aggressively, and then it stabilizes at the top as we get closer to 1. This can be represented by the formula on the screen right here. This is our general probability model. So this model is originally non-linear, but can be linearized by the logit transformation. So we're going to use pi over 1 minus pi. Yeah, there we go. So we're going to use pi over 1 minus pi, which is going to be equal to e, all raised to the beta sub 0 plus beta sub 1 times x sub 1. And we're going to add up all of our terms up to our arbitrary beta sub p times x sub p. Right. So when we take the natural log of both sides of this equation right here, we're going to come up with a more simpler equation, which can be helpful in using for computation, since we don't have to deal with e or anything like that. So once we take the natural log of the odds ratio, we're going to be able to come up with a formula of beta sub 0 plus beta sub 1 times x sub 1. And we're going to add up all of those terms up until our arbitrary beta sub p times x sub p. So logistic is more appropriate for linear regression fitting, since the range is between negative infinity and positive infinity. So we're always going to want to use this formula right here, since it's simpler and easier to use and understand, and we don't have to worry about raising e to anything or anything like that. All right. So section 12.4 was an example of estimating probability of bankruptcies. All right. So they were looking at data from 33 firms that went bankrupt and another 33 firms that remained afloat. So a multiple logistic regression model was found using the variables x sub 1, x sub 2, and x sub 3. And they also had a response variable of y, which, like we saw before, is binary, with the 0 equaling if the firm was bankrupt after 2 years, and a 1 if the firm was not bankrupt or solvent after the 2 years. And the model they came up for in this example was negative 10.15 plus 0.33 times x sub 1 plus 0.18 times x sub 2 plus 5.09 times x sub 3. The change in odds ratio for unit change in the variable x sub j when the other variables are held fitted in this equation, they found that it was e to the beta sub j hat. So that's not really too important here. This is all the important information that they included in this example. Right, so section 12.5 is going to discuss logistic regression diagnostics. So after fitting a logistic regression model, we can then examine for outliers, high leverage points, influential observations, and other differences within the models. Regression packages with a logistic regression option give various diagnostic measures, and some of those are included right here on the screen. So the first one we have is the estimated probabilities, which can be represented by pi sub I to the hat, pi sub I hat, and then I goes all the way from 1 to n. The second diagnostic measure is one or more types of residuals within the logistical regression model. The third diagnostic measure is our weighted leverages, and our weighted leverages is going to be denoted by P sub II star. And this is the measure to measure the potential effects of the observations in the predictor variables on the obtained logistic regression results. The fourth diagnostic measure is a scale difference in regression coefficients. This is denoted by d beta sub I, and I goes again from 1 to n. And then this is the scaled difference in the regression coefficients when the ith observation is deleted. And finally, our diagnostic measure, the last one, is the change in the chi-squared statistics. So this is denoted by dfg sub I again going from 1 to n. And again, this is the change in the chi-squared statistic g when the ith observation is deleted. Oops. So then we can also use the following graphs to be examined for linear fits. So the first one is going to be a scatter plot of our dr sub I versus our pi sub I hat. The second can be a scatter plot of pr sub I versus our pi sub I hat. And the third plot could be our index plot of dr sub I and our d beta sub I, also our dg sub I, and our p sub I star. So again, these are some graphs that can be used to examine for linear fits. Awesome. So we're going to move on to section 12.6. 12.6 is going to determine what variables we should retain. So we're going to look to see if we need all three variables in the bankruptcy data set. So we're going to look at the change in the likelihood for the two fitted models. So first we're going to look at our L with a P input, which is the log of the likelihood when we have P variables and a constant. We're also going to look at L with the input of P plus Q, which is the log of the likelihood with P plus Q variables. And finally, we're going to look at 2 times our L with our input of P plus Q minus our L with our input of P. And this is going to determine if Q additional variables contribute significantly to the model. So in this case, we're going to look at our chi-squared. So a small chi-squared value means that the variable does not add significantly to the improvement of the prediction. And then a large chi-squared value means that we are indeed going to retain the variable. So this test is valid when n is large. So in this case, they're trying to see if x sub 3 needs to be retained in the bankruptcy data. They performed a chi-square test on x1 and x2 and came up with a value of 3.84. And at the 5% significance level, it was determined that x sub 3 can indeed be dropped from the model. So they did the same with x2 and found a chi-squared value of negative 7.902, which determined that x sub 2 should not be dropped from the model. This procedure is good for nested models, which again, nested models are a set of models that can be obtained from a larger model as special cases. So when we do have nested models, this format or way of going about testing variables is indeed a good way to go. And in this case, we also do have an AIC and a BIC value. So our AIC in this case is going to be equal to negative 2 times the log likelihood of the fitted model plus our 2 times P value. And our BIC in this case is going to equal to negative 2 times the log likelihood of the fitted model plus P log n. And in both cases, P is equal to the number of variables in the model. All right, so section 12.7, we're going to be looking at judging the fit of a logistic regression. So a measure like R squared in multiple regression does not exist in logistic regression. In logistic regression, we will determine the number of observations in the sample that the model is classifying correctly. So we're going to find fitted probabilities and sort them based off of if they are above or below 0.5. A high proportion of correct classification will indicate that the logistic model is indeed working well. So in the bankruptcy data, X1 and X2 were both found to misclassify one observation. So we're also going to have our concordance index, and this is going to be represented by a capital C. So our concordance index is going to measure overall correct classification. This is going to be calculated by considering all possible pairs formed by taking one observation from each group. So this is going to be measured in percentages, and this is going to lie between 0.5 and 1. So just to put this into context, in the bankruptcy data, the concordance index was found to be 0.99, which indeed is a good fit. Awesome. So now we're going to move on to section 12.8, which is the multinomial logit model. In logistical regression, models can be used with more than 2 values. Variables can also be ordered and non-ordered. So first, we're going to take a look at the multinomial logistic regression. We're going to have n independent observations, p explanatory variables, and k categories. So first, we're going to take a category at base level, and we're going to have pi sub j equal to our multinomial probability of an observation falling in the jth category. Our multiple logistic regression model in this case is going to be very similar to the one we saw before, except now we're going to have j's in there as well. So we're going to have beta sub 0j plus beta sub 1j times x sub 1I. Then we're going to add up all that until we get to our arbitrary beta sub pj times x sub pi. So pretty similar to what we saw before. We're just adding another variable. So the second section in this, the second subsection in this section was an example of determining chemical diabetes. So they had three categories in this case: overt diabetes, chemical diabetes, and normal. So the three variables in this case were insulin response, steady stable plasma, and glucose, steady stable plasma glucose, and relative weight. So relative weight was found to have insignificant values in each model. The observation is classified to that category for which it was the highest estimated probability. They indeed found that 81% of the observations were correctly classified. This was found to be a good example of multinomial logistic regression due to that high percentage. So the third subsection was ordinal logistic regression. A logistic model with slight modifications can be used in this case. So in this case, we're going to have a proportional odds model. So our proportional odds model is, oops, oh no. All right, there we go. So our proportional odds model is going to be represented by L sub j with an input of x sub I, and that is going to be equal to beta sub 0j plus beta sub 1j times x sub 1I plus beta sub 2j times x sub 2I, all the way up to our arbitrary beta sub j times x sub pi. And the number of parameters estimated to describe the data is fewer in ordinal than in the nominal model. In our last subsection of this section, we're going to go back to the example with determining chemical diabetes. So in this case, they used a natural order of diabetes in their analysis. The model was deemed good, and both variables have a significant relationship. So they found 114 out of 145 subjects were found to have been correctly classified, which equals to around 79%. And lastly, we're going to go over section 12.9, which is a classification problem with another approach. So classification is another method we can use. Discriminant analysis, in this case, is when we are interested in predicting the group membership of each observation. So in this case, we're going to find a linear combination of the predictor variables. We want to separate the two groups as far as possible, and one way is to fit a multiple regression model to the data. So in general, logistic regression does not have to make the restrictive assumption of multivariate normality for the predictor variables. So in this case, they recommend using logistic regression for classification problems. All right, so that is going to wrap up chapter 12 of logistic regression. Thank you guys for watching. As always, if you have any questions, please leave them. Just let me know. And hopefully I'll see you next week. Have a good one.